perfectly fine running program that way, but didn't know how, you know, if you wanted us to do it the other way
Right,
around. So
right.
Figured I'd try to get it to work.
Nice. All right. Well, any questions?
Did we talk about storing items yet?
Yeah, we talked about that on Tuesday.
Okay.
So the idea was to change your max val function to return something like a structure, where that structure contains not only the maximum value but also an array of item counts. So something like this. So have a value which is the actual. Sorry?
I've been prototyping mine a little different for the time being, just to like get something working, because I have it actually returning a max value and I have it caching, but the issue I have is like I always get some wonky value over the inventory I return back. Go ahead.
Okay. So yeah, have you know, something that can store a value as well as a count of each item that gets you that value. And the idea is, you know, counts as an array, one integer per item. And so if to get this value you need, you know, 3 of item 2 and 6 of item 5, then elements 2 and 5 would have values of 3 and 6, right? And all the other elements here would be 0, saying don't take any of those items. So if you do that, then inside your loop, where you're iterating over the items, each time you call max val, right? So you say, let's put in item, you know, I. So let's take the value of item I plus max val of capacity minus weight of item I, right? Well, instead of doing that, right, do some temporary result equals max val of capacity minus weight of item I. And now this thing has not only a value, but it has an item count, right? And so you can do value I plus temp dot value, if that's what you're calling the value part. And so, you know, this solution is equal to that. If this is bigger than best, then keep some, you know, running variable, a struct answer best. And so if this value is bigger than, say, best dot value, then you can say best equals temp to copy, you know, the value from your max val subproblem into your best, and set best dot value equal to temp, or equal to this. So you set the value of this best answer to be, you know, the value you got by putting in item I and adding stuff into the rest of the bag. And then this dot counts bracket I, just bump that up. Sorry, best. So your best answer, which has the item counts to get this max value, just bump up the count of item I if that's where you are in the loop. And now best is telling you how many items you take to get best dot value, which is the best value you found so far. So something like that.
So if it's not exactly like, I mean, I'm using an integer value as a temporary and checking it against this value,
Mm-hmm.
and then it stores it back into the structure if it is bigger.
Okay.
And that should, I mean, it's working and the inventory's working, so that should be fine, right? I mean, that's otherwise that it pretty much follows the same thing.
Yeah, as long as it's working, you're good.
Okay, I didn't know how strict you were on that.
I'm not really too worried about, you know, how you dial in the implementation.
Okay.
as long as it'll give me the correct value and also the correct item counts to get that value, you're good to go.
And then what's the limits on that? Sorry, Lindsay. Like what's like the maximum capacity and stuff like that we can get?
It's written up in the assignment.
Is it? Okay.
So take a look in there, because I don't remember. I think it's 128 items and a 1024 capacity, but double check the PDF.
Oh, okay. Yep, I do see that. I'm sorry.
Okay, no problem.
Okay, perfect.
I'm realizing that when I have an array and struct made for everything that was read into the file so that it's all in memory, but you're also saying that basically we need a second one?
If you're going to try to track the items that give you the maximum value, you're probably going to want a second structure, because you're going to need to return two things from max value. You're going to need to return the actual maximum value and also the count of items that give you that maximum value.
And this could just be put in the .h file too, correct?
The structure definition, yeah.
Okay.
In fact, that would be the ideal place to put it.
Strange. Okay.
You said specifically we could do this all in one file as long as we have a make file too, right? So we don't
Yep,
have to
that's
do...
fine.
Okay.
Yeah, so I'm not going to link to your max val function and such. I haven't given you a prototype for max val. You don't even have to call it max val. I'm just going to use your main program to solve the knapsack problem. So yeah, you've got some freedom there.
I've been mostly avoiding the Discord because I want to solve it myself.
Okay.
What I tried to do is a little close to what you've done, but I still end up with funny results. So, time to debug some more.
So in the value only case, right, max val capacity, which returns an int, we suggested, start off with some best value equal to 0, and then do your loop where you basically say if, temp equals value I plus max val capacity minus weight I. If temp is bigger than best, set best equal to temp, and then return best, and do all this thing, only if weight of item I is less than or equal to capacity. So in that pseudocode, right, this is critical. You've got to initialize best to 0 so that if you don't add anything in, right, you're going to return best, and you can take care of that with a base case. But if you're doing this with a structure, and we're going to have, something outside this loop, a best answer, right, make sure you initialize best. Which means setting the value to 0 and setting each of your item counts to 0. So run a little loop from 0 to 127, set best dot counts bracket I equal to 0. Otherwise, these things have random numbers in them, and as you go through, you keep adjusting, random numbers of inventories, and you end up with some crazy inventory at the end. Same thing with the value, set best value equal to 0. Otherwise, it's got some random number, and you end up with just some bizarre number for max val. So make sure you initialize, make sure you run this on the server. If you do this in Visual Studio, it might initialize things to 0 for you automatically. You put it on the server, it might totally blow up. So make sure if you're not developing on the server, make sure you at least check this on the server.
Always.
Yeah. All right, other questions?
We should probably check with other files too, right? Not just the one file.
Yeah, try some other files. We did one in class that easily shows, where a greedy approach doesn't work, so try that. Try something where all of your items are too heavy to put in the bag, so you should get a max val of 0. Find edge cases and play with those.
Oh, so we should probably check if the bag's capacity is 0, then just return, or then don't even use the function.
If the bag's capacity is 0, you can just return 0 right away. Just make sure that, if you're doing the whole item thing, that you return not just a value of 0, but an item count of 0. And really that should happen automatically because, this for loop, we're only adjusting our best answer possibly if the weight of an item is smaller than the capacity. If the capacity is 0, this if statement will never be true. We'll never, adjust our best answer, and we should end up just returning what we initialized it to, which is hopefully, a value of 0 and item counts of 0. But a base case is stops you from having to think of that when you're debugging your code.
Yeah, that's weird because I just put bag capacity 0 and started up, and it gives me some very high numbers for item count and for possible value, or highest value. So I gotta look into that a little bit.
Yeah, make sure you 0 out those item counts in the beginning. And make sure, if you're going to call maxval, save the result of maxval in some variable. Don't just save it in best, right? Because if best is supposed to represent the best possible solution, as soon as I said best equal to maxval, I've trashed best. I've set it to whatever my last call to maxval was. So I'm saving maxval in a different variable, calculating the value I can get using that value, and if that's better than my best value, then I go ahead and I copy temp into best and go on with that. If you don't do that, you potentially keep updating your item counts whether or not that's the best solution, and then you end up with like really big numbers at the end of your loop. Also, don't make things global. Your save array, your cache for answers can be global. Everything else should be local.
You could also make it static, so it's a little more immutable, I guess.
Shouldn't have to be static though. Statics are mostly when you have globals. Oh, your cache array could be static. Yeah, that's true.
That'd probably be better practice in real life too, unless you have like a member variable.
Yeah, yeah. Or allocate it dynamically in the beginning of main, and then it's a fixed memory pool. But we don't have to get fancy for this. We can if we want. All right, let's talk about tree balancing, and in particular AVL trees. And so remember our basic setup. We have a tree with data in it. And our trees have this property where things to the left are smaller than a root, things to the right are bigger than a root. So that's why we can search and do all of our recursion on these trees. And we noted that, the general performance is what we call order log n. And so what does that mean? It means if you have n pieces of data in your tree, it takes you roughly this much work to add, to search, to delete, things like that. The reason that is that if you have a tree with n items in it, the height is on the order of log n. And that happens because each time you add one more level to the height of the tree, you double the amount of stuff in this last row. And so you're adding powers of 2, and that ends up, you know, increasing the total number of nodes by roughly 2x each level that you have. So if you made a tree with 1,023 nodes, it would have a height of 10. Right, so that's where the log n is coming from. These are usually log base 2 if we don't say. But this only works if your tree is, you know, very filled in at the upper levels. And if somebody was running your program from PA4 and putting in data in this order, 40, 20, 30, 10, 60, 50, 70, this would be the tree that you would end up with. Because the 40 would be the root. When you try to insert a 20, you'd go to the left and put it there. When you tried to insert a 30, you'd go left and right, put it there. A 10, you'd go left and put it there, and so on. And you'd end up with this nice full tree. But if you rerun your program and you input your data like this, you get a different tree, right? The 70 goes to a root, the 60 goes to the left, the 50 goes to the left, and so on. And you end up with this thing that technically is a tree, but really looks like a linked list. And the height of a tree like this is basically n, the number of nodes that you have in here. And since the height of the tree is related to how much work we have to do to add, to search, to delete, right? Operations on this tree will be more along the lines of order n instead of order log n. And it's exactly the same set of data, exactly the same code that you're running in PA4, but vastly different performance characteristics. And so without doing some extra work, the performance of a binary search tree is sort of unpredictable, and worst case can be pretty bad. Right? Worst case, your data that you're using to build the tree starts off very close to sorted, and you end up with a horrible tree as a result. So the goal is, you know, for a certain set of data, we would like to end up with a tree that looked like this instead of this. And we can't necessarily control the order in which the data arrives. So how do we modify our add function to build up a binary tree node by node, but have it end up looking more like this, where this is balanced? And so an AVL tree is a way to deal with that question. And the key is going to come down to each time that we add something to our tree, we're going to potentially adjust the structure of our tree. And we're going to adjust it so that it's still a binary search tree. It still has this left-right property, but it will be closer to being balanced. It will take stuff that, you know, is needlessly lopsided on one side and move it into a more balanced appearance. And the basic operation that we're going to use is what's called a rotation. And here's a simple example of a rotation. So here's a binary search tree containing 10, 20, 30. And if you imagine that your tree looks like this, here's a 10, here's a 20, here's a 30. Here's what we're going to do. We're going to take this and we're going to change it into this, 10, 20, 30. And if we do that very carefully, we'll preserve the order, right? The 10 up here should be, you know, to the left of the 20, should be to the left of the 30. If we just sort of take this and move that up to the root and bring that 10 down, we'll have a 10, 20, 30. It's still a BST, but now it's balanced. It's got the same height on both sides, and so on. So we're going to take this and change it into this. And we can sort of visualize this as, you know, maybe rotating about the 20, taking this and going whoop, and now we've got this shape. So that's the essence of what our adjustments are going to be, these rotations. And they sometimes get a little more complicated than that. For example, if 20 had something hanging to the left of it, like let's say we had a 10 and a 20 and a 30, well, we've got a 15 sitting over here. Well, we can't just take that 10 and bring it down here, because what's going to happen to the 15? We're asking 20 to adopt 10 on its left, but 20 already has a child on the left. So we'd need to do something different there. And so what we're going to do in this case is we're still going to bring the 20 up to the root. We're going to leave 20's right child as it is. We're going to take the 10 and bring that down to the left. So it's going to look like this, but where's that 15 going to go? Well, it's got to go somewhere to the left of 20. It's got to go somewhere to the right of 10 because it was sitting in a subtree to the right of 10. But guess what? 10 had a child on its right, and it no longer has a right child, so this is going to be free to pick up the 15.
Well, but don't you end up with the same height?
You end up with the same height, but in this case, if we look at the node, the left subtree has a height of 1, the right subtree has a height of 0, so our heights are within 1 of each other now.
Still balanced.
Whereas over here, the left subtree was null, that had a height of -1, and the right subtree had a height of 1, the difference was 2, so that was unbalanced. This is a balanced tree. So that's our basic plan. Say again?
I've heard this balancing act is quite difficult.
Yeah, it's tricky. It's shaving a gorilla with a straight razor, right? It's easy to do, but you got to be really careful.
Did it lend itself to recursion, or?
We actually don't need to do a lot of recursion for this. So this is going to boil down to basically looking at a series of cases that tell us, you know, how exactly should we take a tree and adjust it to another. And there's actually 4 cases we need to deal with. These are called left, right, right, left, 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 and right, right. The one we've been dealing with here, this is called right, right. And the idea is, intuitively, we've got too much stuff hanging off to the right of a root. And if we have that, we can adjust it by basically taking this 3 and bringing it down to the left of the 4. That's what's happening here. And the only other change is if B had a left child, if 4 had a left child B, we now let 3 pick that up on the right. The children of 5 are unchanged, the left child of 3 is unchanged, and the right child of 4 is unchanged. And so this is one of 4 possible situations, this right-right case. And, yeah, go ahead.
And you just walk through the entire tree this way, but not in a recursive way, more like a stacks or a queues way, like you went over last week, right?
It turns out that if you add a new node to a tree, you can start from that node and work your way up and figure out if and where the tree is unbalanced. And so there's these things called balance factors. It's these little numbers, -2, 0 or 1, 0, -1. We're going to talk about those in a minute. And that's how we're going to know if the tree is unbalanced and where we need to make this adjustment.
Interesting.
Yeah, and I'll show you some code for this when we're done talking about it. So this is a right-right case. This is what we're starting with here. There's a symmetric version, which is left-left. Exactly the same deal, except, you know, stuff is hanging over to the left. So we take this and we bring it down, and we take C's right child, and we adopt it on the left of 5. 4's right child. But there's 2 other cases. So for example, right, left, this is also an unbalanced tree, but unlike this one, which, you know, had stuff to the right and stuff to the right, the right-left case is unbalanced because there's too much stuff on the right, but that right subtree is kind of heavy on the left. And in that case, we can't go directly from here to just a single rotation. We make a rotation on here to change it into a right-right case. In other words, we take the 4 and the 5 and we rotate it like that, so that now we've got you know, something that's heavier on the right, and then we can go ahead and we can do our right-right rotation. So let me talk about balance factors, which is how we know if the tree is unbalanced and where the tree is unbalanced. And then we'll go through some examples of building a tree and making these adjustments, and then we can look at some code. But any other questions at this point?
Is this the red black algorithm that you were talking
No,
about?
so this is different from red black trees. I may try to do a short video on red black trees. I don't know. I haven't decided if I've got time, but this is a type of balanced tree called an AVL tree, which is a different approach from a red black tree. All right, hold on 1 second because something just beeped in the kitchen. I'll be right back. All right.
I've read that there's really different cases to use either. In some cases, it's more preferable to use an AVL tree rather than a red-black tree, but I'm not fully understanding why that is.
So the general notion is an AVL tree is always going to leave us with a balanced tree, in the sense of balance that we talked about for a PA4. Where the left and right are balanced and the heights of the subtrees are within one. A red-black tree does not guarantee balance in that sense. It actually can have a tree where, you know, the left side has a height of 1,000 and the right side has a height of 2,000. So it can look wildly unbalanced in the true sense of balance, but it puts a bounds on the ratio of the heights of the left and right trees. And it basically says they're always within a factor of 2 of each other. So 1,000 on one side, 2,000 on another side would be allowable. And this will still give us really good performance, but it's allows for kind of a sloppier looking tree. It's a looser sense of balance that still gives us, you know, our desired performance.
So,
Yeah.
hang on a second. Let me, if I heard that correctly, it's always going to be within a factor of 2 on a red-black tree.
Right.
Interesting.
Whereas an AVL tree, it's always within an absolute difference of 1.
Okay.
So if one side had a height of 1,000, the other side would have to have a height between 999 or 1,001. The coding for a red-black tree, I believe, is more complex. There's a lot more special cases involved, and some of the adjustments are trickier. Plus, you know, you need a color bit on each node to indicate whether it's red or black. So I don't know what exactly the different use cases would be, but I think AVL may be faster because you're not doing as aggressive a balancing at each point. But I've never used AVL trees, so I'm just speculating. Sorry, I've never used red-black trees.
I've heard they're extensively used in .NET with their hash system.
That would make sense.
Out a little bit.
Yeah. So here's a balanced tree. Here's a tree that's also balanced. Here's a tree that's also balanced. But if I add another node right here, it's still going to be balanced. If I add another node over here, it will probably be unbalanced. So with AVL trees, the idea is you're starting with a balanced tree, and let's say we're just adding nodes to it. Each time that we add, we want to potentially adjust our tree to keep it balanced. So we want to be able to figure out after each addition or deletion if the tree is balanced. So we calculate for each node what's called a balance factor. So So this is a per node calculation. And kind of arbitrarily, balance factor is defined as the height of the left subtree of the node minus the height of the right subtree. Everything that we're doing, we could do this with these things reversed. It would all still work, but it would be backwards compared to the standard that people use. So balance factor we're going to define is the height of the left subtree minus the height of the right. And it's not an absolute value. It could be positive, negative, or 0. And it's a simple formula, but it can be surprisingly tricky to calculate correctly because our brains look for shortcuts. So let's look at this node right here. So what do you think the balance factor of this node would be?
Would it be 0 because the height of the left subtree and the height of the right subtree are exactly the same?
You got it. So the left and right subtrees of this node are null. Null trees have a height of -1. So the balance factor is -1 minus -1, which is just 0. And the same thing is going to be true here and here also. So what about this node? What would the balance factor of this be?
Wouldn't that be also 0? Be 1
Yeah.
minus 1?
Yep, it would be actually 0 minus 0. So the left subtree is a single node, which has a height of 0. The right subtree also. So the balance factor will be 0 minus 0. That's also 0.
Oh, so null is null is -1, but if there's only one node, then it's 0. So it's
Yep. So the height of a null is -1. The height of a single node is 0. The height of something with one level would be 1, and so on.
What about the node just to the right of the one we were looking at? Wouldn't that be like a -1 because it has...
This one?
Yeah, that one.
All right. So what's the left subtree look like?
It'd be a height of -1. Sorry, 1.
So what's the left subtree of this node?
It's just a single node.
It's a single node, and a single node has a height of 0. So the height of the left subtree is 0. What's the right subtree of this node?
-1, right?
Right, it's null, so it's -1. So the balance factor is 0 minus -1, which is +1.
And it has to be less than 1 to be balanced, right? So it can't be 1?
To be balanced, every balance factor should be 0, 1, or -1.
Oh, so that would still be considered balanced.
So that's still considered balanced.
Okay.
And then what's the balance factor up
One
here?
is inclusive or not?
Yeah, it can include 1 and -1.
This is so confusing.
It is. I mean, like I say, it's a really simple formula, but it's really tricky to apply it correctly.
Is balance factor useful for going through the balancing? So like every time you insert a node and you need to make sure the tree is balanced, you're going to look at the balance factor of certain nodes, right?
Exactly.
Okay, gotcha.
So what's the balance factor at the root?
0.
Right? So it's the height of the left subtree, which is 1, minus the height of the right subtree, which is 1. That's 0. So this tree is balanced. If every node had a balance factor of 0, it would be what I call perfectly balanced. It would mean that every node had either no children or 2 children. It's like completely filled in. So let's try a different kind of tree.
Now, will we ever write a program to check if it's perfectly balanced, or do we not ever get that specific?
I'm not going to make you write a program to do that. but you'll probably do that at some point in
the
your
field
in the field or maybe at a university.
Okay.
I might have to set up a challenge for myself of a break to do this.
It's not a bad thing to do, and I'll show you some code later on. And when I started teaching this a few years ago, I gave myself the same challenge and wrote some code to actually do the balancing, and it wasn't as bad as I thought it was going to be. And it's kind of confidence boosting once you get it to work. All right, so let's find the balance factors for this tree. So this node right down here, what's the balance factor going to be?
Wouldn't it be 0?
Yeah, leaf nodes are pretty much always going to be 0. If there's nothing to the left or the right, both of those trees are null. They both have a height of -1. -1 minus -1 is going to be 0. So I'll start putting my balance factors in parentheses here. And then what about this node right here?
1.
Right, so it's 1. The height of the left subtree, that's a single node, is 0. The right subtree's null height is -1. So this is going to be 1. And we start to kind of get this intuition of like, well, let's just count how many leaves to the deepest root, deepest leaf here and here, and let's see what the difference is. All right, so this one's much trickier. Balance factor of this node.
-2.
So how do we get that?
You got -1 on the left. Hold on.
I think it would be 1, right? 1 on the left subtree, -2 on the right subtree. No, oops.
It would be -1 there, and then 1 on the right, so it'd be 0? Is it 0?
So we're looking at this node, right? So what's the left subtree of that node?
Oh, I guess that one's a 0.
Right, it's just this thing. It's a single node which has a height of 0. And then the right subtree of this node is this thing, which has a height of 1. And so this has a balance factor of -1. Alright, this is a leaf node. This will still be a 0. This will be a 0. This hasn't changed from up here, so the left subtree has a height of 0, right is -1, so this has a balance factor of 1. And then what about the root?
Wouldn't it also be a -1?
Mm-hmm.
Because the right tree is slightly larger.
Yeah, right tree looks like this, that has a height of 2. Left tree looks like this, that has a height of 1. 1 minus 2, that's -1. So hey, it's still a balanced tree. All right, let's.
If the balance factor is anywhere greater than -1 to 1, then you know it's unbalanced, right?
Yeah, anything bigger than 1 or smaller than -1 tells you it's unbalanced.
Gotcha.
So let's add one more node over here to the left. Alright, so what happens? This is still 0 because it's a leaf node. But this node now, we've got one node over here, we've got nothing over there. This will be a balance factor of 1. And this node, what will be the balance factor here?
It's going to be 0, because it'll be -1 on the right and 1 on the left.
So it's...
Or I'm sorry, -2.
So it's -1 on the right, right? Because the right child is null.
Or no, I got it.
The left child looks like this. What's the height of this?
Well, that'd be 1, right?
That'll be 1. And so this will be 1 minus -1. That's going to be a 2.
Oh, so just 2.
So there we've got an unbalance. And now we need to make an adjustment. And so if we look at our 4 types of adjustments we can make, in each case there's a node with a balance factor of 2 or -2. If we have a node with a balance factor of 2, we check its left child, and it will be either -1 to indicate this case, or it will be 0 or +1 for this case. If we have a node with a balance factor of -2, we look at the right child, and that node will have a balance factor of 1 for this case, 0 or -1 for that case. And those are the only possibilities.
So, if in practice we were going through the adding, we would just first add like we would in PA4,
Mm-hmm.
and then as we're walking back up to the root, if ever we counter a balance factor of -2 or +2,
Mm-hmm.
you do a rebalance.
Yep. Exactly.
Makes sense.
All right, so let's put some numbers on here. Let's do a 20 and a 10 and a 5 and a 60 and a 50 and a 90 and an 80 and a 70. So we've got the same shape as this tree that we've been working with. And so this has a balance factor of 0, 1, and 2. And so, I'm supposing that we had this tree and we just added a 70, and now the thing is unbalanced. And so we need to do an adjustment. So here's our node with a balance factor of 2, so we're in one of these 2 cases. Let's check the left child of this node. It has a balance factor of 1. That tells me we're in the left case. So we've got too much stuff to the left, and that subtree is heavier on the left. And so we're going to do this kind of rotation where we take this node, right, which has a balance factor of 1, that's the 80, that's going to become the root of this little subtree. So the adjustment is being made just on a piece of this tree, right? We're focusing our attention on this thing right here. And we're going to change it from this into that. And it could be that, there's other stuff hanging off of here, or hanging off of here, or here, and so on. And so in this picture, right, the node with a factor of 2, that's called node 5. It could have something on the right that's a subtree called D. It's hard to see that, but that's a D, and a C, and a B. And so the node with a balance factor of 1, that could have a subtree called C, and the 70 could have subtrees of A and B. And the algorithm says, change your tree to look like this. Take the node with a balance factor of 1, move it up to the root, take the thing with a factor of 2, bring that down to the right of 4. That node's right child is still D. Its left child is 4's previous right child, C, and then this node just goes along for the ride. It's still here on the left of 4, and it's still got its subtrees A and B. Well, we don't have a lot of subtrees here, so this operation is pretty painless. It's going to go 20, 10, 5, 60, 50, but this is going to do this rotate, where the 80 is going to come up to the root, 70 will stay on the left, and 90 goes to the right. And now if we recalculate balance factors, it should look like that. And so this is a balanced tree. So let's take our unfortunately sorted data that, you know, would normally give us a big long skinny tree that looks like a linked list, and let's build this up and use our tree rotations to try to make a balanced tree. And so our data that we're going to insert is going to be, you know, 7, 6, 5, 4, 3, 2, 1. It's our usual data. So the first node that comes in is 7. That's going to be, let me make these multiples of 10. So I don't get them confused with these nodes that are numbered 3, 4, 5. So our first node that comes in is 70. That's going to be the root of the tree. The second node that comes in is 60. That's going to go to the left. And this will still be balanced. This will have a factor of 0. This will have a factor of 1. So then we get a 50, and that's going to go to the left of 70. The left of 60 is going to look like this. This is going to have a factor of 0, 1, and 2. This is unbalanced. And it's unbalanced in the left-left case. And the way we restore balance is move the 60 up to the root and rotate the 70 down. So this will change into a tree that looks like this. Nice and balanced now. Now we get a 40. 40 is going to go to the left of 60, left of 50. That's going to look like this. This will still be balanced. Factor of 0, factor of 1, factor of 0, factor of 1.
So in this case, are you just checking after each addition?
Checking after each addition. Yep, exactly.
Okay.
And if you don't do that, you can't use these rotations. They're not guaranteed to restore balance, so you have to keep up with it as you're inserting.
So in this case, you'll have like 3 functions. You'll have like a check if it's balanced. You'll have like a restructure one, and then an add, obviously.
Yeah. And basically every time I add, I'll do that check, and then I'll do the adjustment if necessary. And the same thing for deleting.
Gotcha.
All right, so let's bring the 30, and it goes to the left of 60, goes to the left, goes to the left, comes out over here. This is not going to be very well balanced anymore. This will be 0, 1, this will be 2, and if I were to calculate these, this would be 2 and this would be 0. But really, once I find an unbalanced point here, this is the thing I need to deal with now. And again, it's a left-left case, 2 and 1, so I'm going to bring the 40 up to the root, bring the 50 down. So this is going to rotate into the following tree. 60 will stay as the original root of the tree. There's a 70 on the right. But this 50, 40, 30 is going to change into a 40, 30, 50. All right, then we get our 20, and that's going to go left, left. That'll come down here. And this is also going to be unbalanced. So this will have a factor of 0, 1. This will also have a factor of 1. But the root's going to have a factor of 2. Alright, so now it gets a little more interesting. We've still got a left-left case, but our rotation will have to be a little more delicate, because we've got some other stuff hanging around. This is something I can't do with a whiteboard. Alright, so there's our tree. We just inserted the 20. We're in a left-left case. This has a factor of 2, this has a factor of 1. So the adjustment we make is the following. This root node is going to come down on the right. So we're going to have a 60 and a 70. The left child of the 60, that's going to become the new root of the tree. So our 40 is going to become the root. The left child of 40 will still be whatever its left child was. So that'll still be a 30, and this will still be a 20. But if 40 had a right child, which is called node C here, C gets adopted by the previous root on the left. The previous root was a 60, so 60 is going to adopt 40's right child, which is a 50. And so this left-left rotation changes this tree into that tree, and that's balanced again. Alright, one more number to insert. Let's insert a 10. And so this will have a balance factor of 0 and 1 and 2, and there's an unbalanced point, and it's another left-left case. And here the rotation is pretty simple because this child of the unbalanced node doesn't have anything on its right, so C is null, right? And the node that has the unbalanced factor doesn't have anything on its right, so D is null. So this simply changes into the same tree, except we do a rotation on this piece. We bring the 20 up to the root, leave the 10 on the left, and pull the 30 down to the right. And so there's the tree we end up with by inserting our numbers in reverse order. And it's that beautiful, nice, full, fluffy, balanced tree that, you know, we've been drawing since the beginning. Even though the data came in a very different order, which by itself would have given us a tree that looked like this.
It seems like deletion might be hard, if not an O1 maybe, in terms of complexity. Like, if you were to delete a node, you'd have to search through that entire subtree to make sure everything's balanced, right, from the leaf nodes up.
Yeah, but when you delete, you're deleting a root node, right? We're always deleting a root.
Okay.
And so the balance factor of that root will change. The balance factor of the children should not change, except that, you know, we've moved a node out of a subtree. So let's work through one example of the left-right case, just for completeness. So suppose I've got a I've got a, well, I'll just pick on values that match up this problem. So I suppose I have a 50 and a 30 and a 40. And, you know, maybe I've got some other stuff hanging off here, subtrees A, B, C, and D, and so on. But in this case, this has a balance factor of 0. This is -1. This is 2. Okay? That difference in sign, the 2 and -1, or the -2 and +1, that tells you you're in this left-right or this right-left case. In this case, it's a left-right case. And the first thing we do is we make an adjustment on this part of the tree, not to balance it, but to change it into a left-left case. So the adjustment we make between nodes 3 and 4, we basically swap them, bring 4 up and bring 3 down to the left. So this is, you know, here's 3 and 4, we're going to do that. We're going to put 4 up at the root and bring 3 down to the left. And so that's pretty easy in this case. We're going to end up with just 50, 40, 30.
Are these pictures on the website somehow?
I've got to post this still on Canvas. I pulled this off of Wikipedia a few years ago. So I'll post that up. I forgot to do that yesterday. Alright, so we'll put the 40 up here, we'll bring the 30 down, and now we've got, you know, an unbalanced tree, but it's a left-left case. And so now we do this rotation, and we would put the 40 up to the root, leave the 30 on the left, bring the 50 down on the right. And so this gets changed into that. All right. Let's go ahead and take a 5-minute break. And then we'll come back and I'll show you some code that implements these changes. And it's not super critical to understand this code, but I want to kind of show you one approach to taking, something potentially complex like this and making it manageable in a C program. So I'll show you a version I made of PA4 a while back that included balancing the tree. So we'll run through that, and then we'll switch topics after that. So let's go ahead and do a short break. Let's come back at 14:07. All right, so I'll be back in a few. Wow, I'm super late. I gotta close these. All right. Any other questions on trees?
Are we still going to touch on red blacks a little bit, or?
I'm thinking if I find the time, I will make a standalone video on that. Because it's a topic I'd like to understand better, but I don't think we have time for it in class. But I might try to make a video on it because it's always something I've either skipped or sloughed over in lecture, and it would be fun to actually like do a decent presentation of it.
What's the time complexity for balancing a tree, and how can you be sure that it's worth the trouble?
I think it's order 1 or maybe order log n. It kind of depends how far up you have to go to find the unbalance point. But worst case, you have to navigate up to the root, which would be log n, right? Because that's the height of the tree. And then, you know, to do those rotations, that's just a fixed amount of time. It's just a bunch of assignment statements. And so I think it's no worse than log n, and if you're doing it as part of the add or delete, which are also log n, it's just a multiplicative constant. So the whole thing, adding plus balancing, would end up still being log n, which is pretty sweet. All right, well, let's eyeball some sample code, just for kicks. And my camera did not die. Let's see. Ooh, that's weird. Let me find my sample code. All right, here we go. All right, so let's take a look at a version of PA4 that also keeps things balanced. So there's 5 additional routines. There's an adjust routine, which will perform these rotations, and that will use these 4 routines: left, right, left, and right, to do the appropriate rotations. And so we also need to calculate balance factor. So here's a routine called balance factor that if the root of the tree is null, then the tree is empty, so the balance factor is 0. Otherwise, it's the height of the left subtree minus the height of the right subtree. So that's straight out of our definition. And then here's the adjustment code. So if the root of the tree is null, right, the tree is empty, we can't have, you know, any of these cases, so we're just going to return right away. Otherwise, I do the following 2 checks. If the balance factor of the root is 2, and the balance factor of the left child is 1, then I'm in this left-right case. Right? And so I call left-right on root, and I save the result in root, and that will do this rotation if necessary, if we had a balance factor of 2 and minus 1. If we do that, we'll end up with a balance factor of 2 at the root and 1 or 0 at the child. And so my next statement is if the balance factor of the root is 2, then I know that either I was in the left-left case to begin with, or I was in the left-right case and now I'm in the left-left case. So all I have to do is see if the root node has balance factor 2, and if it does, I know I need to do a left-left adjustment. So I call left-left on the root, and I save the result. And then the same pair of statements on the right. If balance factor is minus 2 and the right child is 1, that's the right-left case, so I call right-left. And then if the balance factor of the root is minus 2, I'll call right-right.
So, quick question
Mm-hmm.
about what you were talking about earlier. I think it just slipped past me, where we were like talking about delete and how you always delete a root node and the balance factors of the children don't change. So
The balance factor of the left subtree's nodes could change because you're moving something out of there to take it up to the root.
right, and then you just keep readjusting until you have that balance factor every time you replace the roots, right?
Yeah, so when I do my deletion, and this is just, you know, a tree of integers. So if I want to delete the root node, I for example see if there's nothing on the left. If there's nothing on the left, I just move the root down to the right. But before I return, I say let's adjust the tree at that point. If there's something on the left and that subtree has nothing on the right, then I do that case 2. I make the left subtree's root, point to the root's right on its right, and before I return the new root, I call adjust. The general case, we move to the left subtree's root and we traverse down to the right till we can't go any further. We do all of those funny connections, and then we return the root of the new tree. But before we do that return, we go ahead and we say adjust. Otherwise, we make a recursive call, right? So if the data sits to the left, we go ahead and delete from the left, and we put that on the left node of the root, and then we adjust that thing that we just put on the left, and then we adjust the root. And same thing on the right. And then insert is similar, right? If you're going to the left, you're going to insert to the left, but before we return, we adjust the tree at that insert point. Otherwise, we insert on the right. If the tree is empty, we just create a new node, and we know it's going to be balanced, so we don't have to adjust. So then everything comes down to just these 4 cases: left, right, left, left, right, left, and right, right. And here's, you know, a picture shamelessly ripped from Wikipedia of what's going to happen when we do these adjustments. So this first piece of code is going to change the left-right case into the left-left. So that's what left-right does. And it's a really short routine, but it's packed full with lots of stuff, right? So I use lots of temporary pointers, and this is really the point of going through this at all. I'm using temporary variables. I'm making nodes called N5 for node 5, node 3, node 4. Let me label these. This is a 3. This is a 4. This is
I
B.
really like how in most
C,
of your comments you always
D.
have a little ASCII drawing.
Yeah, they're helpful. I think they're helpful. So I've got node 5, node 4, node 3. I've got A, which is a subtree. I've got D, which is a subtree. B and C are subtrees. So I've got all of these variables declared as nodes, and I initialize them to null, so that, you know, if there's nothing to the right of 4, I don't have to set C to null. It's just automatically. That's the default value. And then N5 is the root that I'm trying to adjust, right? That's the place where I found a balance factor of 2. So I set N5 equal to root. I set D equal to N5's right child. Okay. Now I know root is not null. because I'm never going to call left right on null, right? If the root was null, I'm not going to do any of these checks. I'm going to return right away. So I know that n5 is not null, right? Because root's not null. So I'm allowed to look at n5 right. n5 right could be null. D could be null. That's okay. I can still assign n5 right to D. And I can assign n3 to be n5 left. That's totally legal. But n3 could be null. And if n3 is null, I don't want to try to do something with n3 left. So all of this is in a conditional. If n3 is not null, I'll set a equal to n3 left. That's totally legal. Even if a is null, I can set a to null. And I'm going to set n4 to n3 right. But then again, I don't want to do anything with n4 left and right unless I know n4 exists. So if n4 is not null, I'll set b to n4 left and c to n4 right. So now I've set up these local variables to correspond to each of these nodes or subtrees in this picture. And now all I got to do is build a new tree that looks like this using those pieces. And that's what this does. So n5's left child should be n4. That takes care of that. n4's left child should now be n3, right? So n4 used to have b on the left. It should have node 3 on the left, but I'm going to make sure n4 is not null. So if n4 is not null, have n4 pick up n3 on the left, and have it pick up c on the right, which it already had on the right, but you know, I'm just kind of blindly following the algorithm. And then if n3 is not null, I'm going to pick up a on the left and b on the right. Well, it's already got a on the left, but b is a new one, so I'm going to say if n3 is not null, n3 right equals b. And the root of this tree is n5, and so I return that. So all the stuff we've been doing for the past 45 minutes, right, it's just this chunk of code. That's the left-right to left-left case. And then if you're in the left-left case, we're going from here to a balanced tree. And it's the same thing, except it's a little simpler, right? Set up some variables for each of these nodes. Set n5 to the root. D is n5's right child. N4 is n5's left. If and we know n4 is not null because it's got a balance factor here. If this was null, then this wouldn't have a factor of 2. So I set C to be n4's right, n3 to be n4's left. We're not going to do anything with node 3. It's still going to have the same children, so I don't need to worry about A and B. But the whole adjustment here is take node 5 and pick up C on the left. So we get this subtree here. So n5 left is C. And then n4's right child should change from C to node 5. So n4 right equals n5. Return n4 as the new root. So it's a bunch of assignment statements, and it's all, you know, a question of sort of getting them right. But if you're using lots of variables, and if you have a clear picture what it is you want to do, you're likely to be successful in writing that code. And then the right-left and right-right cases are exactly the same. They're just symmetric. And that's the end of the adjustment code. And a little bit to my surprise, this actually works. So that's kind of cool. All right. The other thing that we want to mention is that, you know, as we do these adjustments, this is all great. This will make the tree balanced. We don't want to disturb the sort order of the tree. And so we want to know that if this was a BST to begin with, it's still a BST at the end. And that we can verify by just kind of looking at what these rotations do to the sort order. So suppose we start off with this tree up here, and we write down the order in which things would be traversed in an in-order traversal. So the first thing that will be traversed is everything in subtree A, followed by the root of the tree 3, followed by the in-order traversal of this thing. Traversing this in order means traverse the left subtree in order. So that's going to be a B, a 4, and a C. So this is going to do B, 4, C. And then we're going to traverse the root node, which is a 5, and then traverse the right subtree, which is a D. So here's the traversal order of our original tree: A3, B4, C5, D. If we adjust the tree to look like this, what's the traversal order going to be? Well, we start off with the left subtree is A, and then we do the root node, which is 3, and then we traverse the right subtree. And to traverse this, first we traverse the left subtree B, and then we visit the root 4, and then we traverse the right subtree. And to traverse the right subtree, this is a C and a D, first we do the left subtree, and then the root, and then the right subtree. And it's exactly the same traversal order as this original tree. And then in the last adjustment, we rotate the tree into this shape, and if we traverse this in order, well, it means traverse the left subtree in order first. Let me fill these in also. So we traverse the left subtree, which will be A3B, and then we visit the root node 4, and then we traverse the right subtree, which will be C, 5, and finally D. And it's the exact same traversal order. So that's kind of a sanity check that doing this traversal, doing these rotations does not affect the ordering of the nodes. So as long as you're starting with a BST, you end up with a BST after you balance. Alright, so let's look at tries. So a binary search tree is sort of the simplest tree we can have without being a list. Every node has 2 children or fewer. And if every node has 1 child, we've basically got a linked list. So BST is a pretty simple version of a tree. A trie is way on the other side of the complexity spectrum. And a trie will typically look like this. We'll have a root node, and it will have a whole bunch of children. And each of those children will have a whole bunch of children. And so on. And each of these children will have a whole bunch of children. And so our nodes are really, really wide. And so this takes more memory, right? To have a node that can store, say, 100 children, you need 100 pointers. If a pointer takes 8 bytes, that's 800 bytes per node, not even counting the data that you might actually store in there.
Is there a reason why it's called tries? I assume it just have 3 children instead of 2.
So Fredkin came up with the word try at IBM, I believe, and I forget what he picked that name for. It was a play on the word tree, and I think he actually pronounced it tree, but changed it to try. But I don't remember what the motivation was.
It's not really a specific point to the structure. It's just that's just what they called it.
Well, it's not a particular number of children, but it's going to have a particular way that we're going to process it.
I researched it, and I was under the impression that every node has 26 children exactly.
For the trie that we're going to develop, that's correct. In fact, I've even got a picture of the nodes right here, ready to go. But it's a general concept, and we could have a different number of children per node. Trie was the middle syllable of retrieval. R-E-T-R-I-E-V-A-L. And so it was called tree as in retrieval, but then they changed the pronunciation to try.
Interesting.
if you want to read some interesting biography / research, look up Edward Franken. He's very interesting. I think it's IN. He was an IBM fellow in the 60s, I believe, and did a lot of work on reversible computing, which is potentially a future area of considerable interest in computer science as chips get smaller and power levels drop. It's some interesting concepts in there.
Franken, no L.
Fredkin. Also the creator of the Fredkin gate, which is a reversible gate. All right, so tries, the idea is we've got these really wide nodes with lots of children on each node. Okay, what's the advantage of having wider nodes, something with more than 2 children? The height of your trees is much smaller than with a binary tree. The reason a binary tree packs in nicely is because, since each node has 2 children, when you move down one level, you can double the amount of data that you're storing on this next level versus this level. But if each node had 100 children, right, your next level would have 100 times as much data as the level above it.
And it'd be pretty much just as easy to find that data, right?
Yeah,
because
yeah.
You're already at the node, you just have to have an index.
Yep, you just have to know which of those 100 branches to follow. And so the height would be, closer to the log base 100 of n. And so, if you had a billion pieces of data, let's see, 100, 10,000, million, it would be a height of like 5. Right? And a trillion, I think, would be a height of 7.
It's the reason we're going to be doing it with 26 nodes is more like how autocomplete might work on your phone, where it's guessing the next couple of words given the next possible nodes.
Yep.
Right?
Yeah, that's a nice application of this. So if we've got 26 children or 100 children on each node, how do we search this tree? How do we add something to the tree? With a binary tree, it was simple. If we wanted to look for something and it didn't match the root, it was either to the left or the right. And we could use a binary operator, like, greater than or less than. But with say, 100 children, how do we know which branch we should follow? So here's an example of a trie that's built where each node has 26 children. And conveniently, these 26 pointers are called A, B, C, D, E, F, G. And the idea is, if we're looking for a word that starts with the letter C, it's going to be stored somewhere in the sub-trie pointed to by this pointer called C. So we're going to follow the C to another node, and that node's going to have 26 pointers. If we're looking for the word cat, now we're going to follow the pointer that we call A, the second letter of cat. And that's going to point us to another node, and in that node we're going to follow the pointer called T, which is the third letter of cat. And that's going to point us to a node, and if cat is stored in our trie, that's where it'll be stored. So
So it takes each digit as an index to the next one.
Yeah, it takes each letter in this case as an index to the next node in the structure. So let's build a trie. Let's store some words. So let's start off with the word cat. So we've got an empty trie, and we've always got a root. Maybe the root's null before you do anything, I don't know. But I'm just going to assume there's a root node here. And let's store the word cat. So all our words have uppercase letters, no spaces or punctuation, simplifying. All right, so where should I store a cat in this try? Well, I'm going to start from the root and I'm going to find the pointer C. And initially, all of these pointers are null. Null means it's not pointing to anything, so there's no child from that pointer. So I'm going to look at C, and C is null. So I'm going to create a new node with null pointers, and I'm going to have C point to that node. And then in this second node, I'm going to look at the second letter as A. I'm going to take the pointer A. That's going to be null. So I'm going to create another node, and I'm going to have A point to that. And then I'm going to take the third letter T, and in this node I'm going to look at the pointer T. That's going to be null. So I'll create a fourth node, and I'll have T point to that. So for cat, we have a null terminator when we store it. Instead, what we do is when we get down here, I'm going to set this one variable. This is just a bit called end of string. I'm going to set that to 1. And this is 0 by default.
Gotcha.
So now I have a cat stored in my try. And how do I know that? Well, suppose I want to look for the word cat. I'll start at the root. I'll follow C to this node. I'll follow A to this node. I'll follow T to this node. I'll check the end of string. It's equal to 1. Hey, I've got a cat.
So I know we're doing this so we can see the procedure, but in this case, if we're coding this, are we going to have a for loop that compares the characters for each step?
There's different ways you could do it. So you would probably make your node something that had an array of children. And, you know, it could be an array from 0 to 25. And based on the character, right, if this is a C, then you would use the child array bracket 2. Because C is, you know, the third character of the alphabet. And if for the A, you would do your child array bracket 0. And so it would go together very much like it does with a binary tree. Just a more complex set of children. Instead of just calling them left, right, we probably have an array of them. And you could take, you know, the ASCII value of your letter and subtract 65, and that would give you an index from 0 to 25.
I can absolutely see how you'd use autocomplete for things like this.
Mm-hmm.
Like,
Yeah,
you know,
yeah.
You step on a certain node path, and it might have a list of words that could be ahead of it.
Mm-hmm.
And, you know, what are the likelihoods of those, and then present that to the user,
Yeah.
etc.
So right now, with one word in my try, cat, right? If I start with a C, I know what the word is, right? It's a C followed by an A followed by a T. That must be the word cat. But let's store the word car now. So how do I do that? Well, start with the root. Look at the C. It's not null this time. It's pointing to a node. So let's go down to that node. And let's look at the second letter, A. And the A pointer, that's not null either. It's pointing to a node. So let's go to that node and look at the third letter, R. Well, the R pointer is null. So I'm going to create a new node. And I'm going to have the R point to that node. And then down here, I'll set end of string to 1. Well, bingo, I got a car in my try now.
But what else you could do, if you wanted to, is slim it down to where it only points to possible letters.
Mm-hmm.
So each node, if it points to a letter that doesn't spell a word that's known in the dictionary, then it's not a word, right? Then you save even more space doing that, and if you could even use it for like the red squiggly lines for
Mm-hmm.
you spelled something wrong, right? If it's not in the tree, then it's not a word, right?
Yeah, yeah. That's cool.
That would be a fun challenge. I'm gonna try that.
Awesome. These are really fun to code and to play with. They're memory hogs, which is always fun, and they're a little bit magical feeling. And if you can do a binary tree, you can do a try. You just have to be, you know, a little more involved in defining the children. But they're pretty fun to play with. Let's put cats into our try. So here's a C. It's not null, so it points down here. here's an A, it's not null, it points down here. Third letter is a T, it's not null, it points down here. Let's look at the S. S is null, so I'm going to create a new node. I'm going to have S point to that. And I'll set end of string. Now I've got cats in my try.
So the prototype for one of these nodes, you would have to hard code all the indexes, basically, right? The array.
Mm-hmm. Yeah, and like I say, you would probably make them an array of pointers.
Okay.
All right, let's do GG. So start off at the root node. G is null, so let's create a new node and point to that. Go to the second letter is a G, that's null, so we'll create a new node, point to that, set the end of string to 1. Now GG is in our try. So yeah, if we type a C right now, right, so looking at the root, we know we have some words that start with C and start with a G. If we were doing an autocomplete and someone typed a C, we can come down here. We know the only words we have that start with a C and with an A, because there's only one node here that's not null. So if someone types C, we can go ahead and jump ahead to the A. But down here, we've got two different nodes that have non-null pointers. So there's things that start with a CA that end with R and CA that end with T. And so you can kind of start to do some analysis inside your code for you know, from knowing the beginning of a word, being able to sort of predict what the rest of the word is.
So in that application, if you are using like an autocorrect or whatever, the predictive text, basically you're uploading a database of trees with like the dictionary and like used phrases and things like that, right?
Mm-hmm.
It's going to be your base database, and then you're going to obviously code a way to check.
Yeah.
And then predict the. Okay.
Yeah.
Interesting.
All right, let's look for a cab. So look at the C, it's not null, follow it to another node. Look at the second letter is an A. A's pointer is not null, follow that to another node. Look at the third letter B. B's pointer is null. That tells us cab's not stored in our try. If we look for CA, go ahead.
Is this how they make the, like in Word, when you get, like, oh, this isn't a word? Or it's like spell check, basically?
That might be one way to do it. I mean, there's probably a lot of ways you can do that, but a try is nice because it not only would tell you, you know, there is no cab, but it would tell you, you know, well, but there was something that you know, started with a CA. So if you get pretty far through your try before you discover the thing's not in there, you might know that, hey, they got the beginning of the word right. But, you know...
Because you can, like, right-click on it and it gives you all the words that, like, oh, did you mean these words?
Yeah, yeah.
That's interesting.
You could also try to do it with a hash function. If you came up with a hash function that took words that were close to each other and hashed them to values that were similar.
You just display, like, the list.
Yeah.
Like, whatever's in your hash, just display the whole list. And
Yeah, everything with a hash value within a certain distance of... And I don't know what the actual approach is that's used, like in a typical spell checker. Because, you know, you need to pick up not just, you know, missing letters or substituted letters, but also transpositions of letters and things like that.
yeah, you can hash, like, the first 3 or whatever characters.
Mm-hmm.
And then say, oh, did you mean these things?
Right, right.
Yeah. Because sometimes they're, like, way off, and that, obviously, like you said, it could be just maybe something in their code that says, like, oh, we haven't checked for these cases yet.
Mm-hmm. And I highly encourage, you know, anyone who's interested in this stuff, play around with it, right? These are great problems to tackle to get more practice and experience with coding and algorithm design. And, you know, you can certainly look up algorithms for doing a spell checker. But trying to write your own spell checker and come up with an algorithm by yourself, that would be a fantastic exercise to just kind of, I'm always telling people, write code, write code, write code. But it's hard to know, what code should I write? What does that mean, write code? If you can find a project to work on, that's a great way to sort of have a endless stream of code to practice writing and developing and debugging. And that's just fantastic practice. That's, going to make you so successful in other courses, on the job, things like that. So I strongly recommend, if you're interested in something like that, if you're curious about it, go for it, I've got a student I had in class last year. He just decided to write his own shell. He's at WSU, and I think he's a little bored, actually. And so he just wrote his own shell, his own version of Bash. Yeah, MASH, just to, just to have something to do, something to practice on, something to develop, find some new problems to tackle, things like that. All right, so let's see if CA is in our try, right? So look at the first letter, there's a C, the pointer's not null, follow it to another node. Look at the second letter, there's an A, the pointer's not null, follow that to a third node. We're at the end of our word. If CA is in our try, then this node's end of string should be set. It's not, it's a 0, so CA is not in there. If we wanted to store CA, we would say, okay, first letter is C, that's not null, follow it to a node. Second letter is A, that's not null, follow it to a node. We're at the end of our string. Let's go ahead and set this node's end of string to 1. Well, now CA is in our try.
So that's just saying for that specific set, CA, there is a word for that. So if it's 0, it means that that's not a word, it's just like part of the algorithm.
Exactly.
Okay.
All right, so a few details on here, right? First of all, deletion is a pain. And the easiest way to delete is just clear the end of string flag. So let's say we want to get rid of cat, right? So we want to delete cat. Start off with the root node. There's a C, it points down here. Here's an A, it points down there. Here's a T, it points right here. If we want to delete cat, just set this end of string flag to a 0. And now if we search for cat, it's not going to find that. So that's easy to do, but it's potentially inefficient. Now, we need this node to be around because, we have cats stored, which is what this S pointer is referring to. But if we did not have anything else that this node was pointing to, we could get rid of this whole node as long as we get rid of the things that are pointing to it. And so you can get into an algorithm to delete nodes that you no longer need. But that's a level of complexity I'm not going to go into. But you can always delete a word by just clearing the end of string flag. But if your goal is to, harvest data and just keep building it up into a big structure, this is a really nice data structure for doing that. It's pretty clearly memory intensive, right? If we don't have a lot of replication between words, we have basically one node per letter of each word that we have stored in our try. Now, cat and car, we only have one node for that first C. But, theoretically, if you've got, 100 words and they each have 5 letters, order 500 nodes, right? And these nodes are really wide, lots of memory. This takes a lot of memory. But the search time is really, really good.
And if you were, doing that auto checker thing where you need 26 letters per structure, that's 8 times 26 bytes just for the part that points to the next.
Yep. Yeah. Which adds up. I mean, it's not a big deal today, but when we had 16K of memory and that was it, that's a pretty significant chunk of it.
So we were talking a while back when we were doing hash functions that Google that's kind of how they did it, right? They're doing hash, they're not doing trees.
I have no idea how Google does what they do.
Okay.
That's a bit of their secret sauce.
Gotcha.
They're certainly doing,
Could have done that.
yeah, they're almost certainly doing something associative, which suggests some kind of hashing maybe. But I don't know how much of their algorithm they actually tell you about, and how much is protected. I think if you go back to some of the earlier work when Sergey and his friend were working out the original ideas, I think you can probably find some details there.
Yeah, I would imagine you're signing some kind of non-disclosure when you get a job there.
Yeah, definitely.
I was gonna ask you, since we've been talking about trees a bunch,
Mm-hmm.
will we ever talk about, maybe at least for a little bit, how you can kind of use hashes with trees and how that usually plays out?
I wasn't planning to, but sort of the two first ideas that come to mind is one, you could do like we did with our hash assignment, but when you have a collision, instead of having a linked list in each node, you could have a binary search tree for each entry in the hash table.
And that would create like a forest, you said, right?
That would be like a forest, yeah. But it's not clear that would buy you a lot, because if you cut your data down by 1,000, right, by having 1,000 entries in your hash, you divide your data by 1,000 while you're getting rid of 10 operations, basically, because that's 10 lower levels of the tree.
It seems like what you could do, maybe in the case of like an autofill, what you'd do is say, hey, each one of these tries has like a cap on how many words they can store in them, so you don't have to go too deep into them.
Mm-hmm.
And if there's a duplicate, ignore it, right?
Mm-hmm.
But if you run into a collision and the tree is already too big, then you find another spot to store it. And that way, when you're searching it, you don't have too much trouble, right?
Yeah, you could do something like that, definitely. Here's the other weird thing about these tries. Is the word cat stored anywhere in any of these nodes?
Depends on if each node stores a string of what it already is, right? Maybe?
Yeah. I mean, I don't have to have any character pointers anywhere in this structure. I have pointers to nodes, and I have, a single bit that's a 1 or a 0. And that's it. There's nowhere explicitly that the string CAT or CAR is stored anywhere. The string is stored kind of implicitly by the search pattern you follow till you get to a node with an end of string bit set to 1. And that's kind of interesting. That's taking data and encapsulating it in a process, which personally I think is part of how the brain works. I think the associative part of memory is that we don't just store bit patterns that we retrieve. We store a process that when we run that process, it replicates conditions from when a memory was created, and so we think we're remembering something. And that's a little bit what it feels like is going on in here. You don't find these strings stored anywhere, but that information is contained in there, and you can get to it through the process of following pointers.
So, in my Java class, I talked to you last week, I think, about the Huffman coding.
Mm-hmm.
Is this kind of how that works? It's following the path and just returns what the path is instead of...
Huffman coding doesn't actually use tries per se, but it will have maybe a similar feel, where you might think of it as building a tree, but where you're branching off based on groups of symbols.
Okay.
So it could be a similar feel.
Okay.
All right, so that's probably enough about tries to do your try quiz, and I think you've got enough about balanced trees to do the balancing tree question on the quizzes. So let's talk about sorting, and I want to talk about sorting today, and probably a good chunk of Tuesday. And then that'll probably do us for the quarter. We'll spend Thursday doing some review. So let's look at some sorting questions. And sorting is you've got a bunch of numbers and you want to order them basically, right? So we can do this a number of ways. And there's a series of different algorithms we can use to teach a computer how to sort numbers. And all these algorithms will work, but you can find a whole book of just different sort algorithms. So why do we have all these different sort algorithms? One reason is speed, right? And again, we're not so much interested in raw speed as we are in order of complexity. How does the speed change as the amount of stuff we want to sort changes? In particular, if I have twice as many numbers, will my algorithm take twice as long? Will it take 4 times as long? Will it take 1 point something times as long? So we're interested in speed. We're also interested in complexity, right? If you have to code a sort algorithm for an embedded system, like a microwave oven controller, you may not want to spend the entire amount of program memory coding up a sort that's super fast just so you can sort 10 things. So you might go with an algorithm that's like really, really simple to code, maybe not the most efficient algorithm possible, but plenty fine for what you have to actually do. On larger systems, right, there's different algorithms based on how much you want to move your data around. If you have data stored on a magnetic tape, so you've got a spool of magnetic tape 5,000 feet long, and you have data stored on that, and you want to sort it, and you want to create a new magnetic tape that has the same data but sorted, say, in increasing order. Well, magnetic tape is really funny, right? You can get to any point on this tape, but you have to fast forward or rewind. I don't know how many people here ever had cassette tapes when you were kids listening to music.
Yep.
But you got your favorite song, and it's like at the end of the tape you got to fast forward and wait for it, right? Same thing with magnetic tape for a computer. Trying to read sequential information very, very fast. You can spin this tape really, really quickly and read the data as it's spinning. But if you need to go back and read something from another part of the tape, it's really slow. So if you have data stored on a magnetic tape and you want to sort it, you would use a different kind of algorithm, preferably one that didn't need you to bounce around, from one point to another a whole lot. And so lots of different sort algorithms that have different characteristics that are, better or worse suited for different situations.
So you're like getting to defragmentation here maybe a little bit?
Yeah. So hard drives are similar. We can do random access on a hard drive better than we can on a magnetic tape, but we can go directly to a cylinder on a hard drive, but we still have to wait for our data to rotate into place. And so if we store data in an unfragmented file, right, once we get to the starting point, we can just keep reading off the information like spinning a vinyl record, right? If your file's fragmented, then you need to bounce around to different locations, and the buzzword would be seek time, and seek time is a performance killer on hard drives. Of course, if you got a solid state drive, it's less of an issue.
But even solid state drives contend with that on some level.
Yeah, so solid state drives, you still have to read in like a chunk of data maybe, depending on the technology. And so you'd like your data to have some locality to it. These are all topics in the realm of computer architecture, which is a great class to take. And you get some of this in Engineering 270 here. All right, so what's the first sort that that we usually learn. What's a sort that people here know?
Bubble.
Bubble sort.
Short.
So bubble sort is usually the first
Word
one.
Radix sort.
Radix sort. So we're going to do all of these. We're going to do bubble sort, insertion sort, selection sort, merge sort, quick sort, radix sort, and heap sort. So we're going to go through several different types of sorts. And analysis-wise, we're going to be thinking about order of complexity. How much work do we do inside these sorts? So how's a bubble sort work? Bunch of numbers, and we want to sort them, and I'm just going to consistently go from smallest to largest, so we don't have to keep saying it. So bubble sort, we start off with, say, an array of data, and we make a series of passes through it. And each pass, what we do is we compare each number to the number after it. And we try to make sure that pair of numbers is in the correct order. In other words, the first number is smaller than the second. So we look at a 2 and a 4, those are in the correct order. We look at the 4 and the 1, those are reversed, so we'll switch the 1 and the 4. We look at the 4 and the 3, those are reversed, so we'll switch the 3 and the 4. Look at the 4 and the 6, those are in the correct order. Look at 6 and 9, that's in the correct order. Look at 9 and 7, that's reversed, so we'll swap that. And after one pass, this is what our data looks like. And it's still not sorted. We've got a 2 followed by a 1. That's not right. But what we know with a bubble sort is after one pass, the largest number has sunk down to the bottom. So if you do this trying to move the smallest number to the top, it's like bubbles floating up to the surface of water. So that's the bubble sort version, but this is like a rock sort. So the heaviest things are sinking down to the bottom. All right, make another pass through this data. So the 2 and the 1 are in the wrong order. Swap those. 2 and 3 are correct. 3 and 4 are correct. 4 and 6 is correct. 6 and 7 is correct. 7 and 9 is correct. The 9's never going to move. Since that's the largest thing in the array and it's at the bottom, it's never going to swap places with anything. But after a second pass, we're guaranteed the second largest number is now in the second position. Well, we got lucky here, right? After 2 passes, hey, the entire array is sorted. That doesn't usually happen. But it could. It could be that our data is sorted to begin with, in which case, without doing any work, our data would be sorted. But in this case, you know, we made 2 passes and our data is sorted. But it could be that you know, we would need to make more passes. All we're guaranteed after 2 passes is that these 2 numbers are in the right location. Well, if you have n numbers, you need potentially n passes. Approximately n. It's actually n minus 1. But you need approximately n passes to guarantee that everything is in the correct spot. So how much work do we do in making one of these passes through our array? That turns out to be order n.
But the passes would be order n squared, right?
So each pass we do order n work, meaning, you know, if we've got 100 numbers, we're going to do about 100 operations. We're going to compare each number to the number after it, possibly swap them. If we have 100 numbers, we're going to do that 100 times. So each pass takes approximately n operations, and we have approximately n passes, and so this whole thing ends up being order n squared.
I have one question here. I've thought about this, but I'm not exactly sure because I've written a bubble sort, but only when a professor gave me a bubble sort to write.
Okay.
And I was curious, like, let's say you had 1 to 9 here as our data set. In order to actually get that 100 operations, you'd need to have it, like, in complete reverse order, right? Like 9, 8, 7, 6, 5, 4, 3, 2, 1 in order to get the full, like, 100?
I think so, yeah.
Interesting.
if your data starts off like that, then yeah, I think you'll end up with that after your first pass, that after your second pass, that after your third pass, and so on. So yeah, I don't know if that's the only case where you'd need all n steps. But that would certainly be a case. All right, so nominally order n squared for this, and you know, it codes basically as a pair of nested loops. And order n squared, typically you've got a pair of nested loops. So for pass equals 1 to n for data, or you know, for I equals 1 to n. Compare data I with data I plus 1 and swap if they're out of order. So this thing happens n times in this loop, and this whole loop happens a total of n times. So that's order n squared. I'm being really sloppy with the edge cases here, right? I'm indexing from 1 to n instead of 0 to n minus 1. And since we're comparing a number to the number after it, we only need to go up to not the last number, but the number before the last, so that we compare that with the actual last number. And we only really need to do n minus 1 passes, because once we sort the n minus 1 largest numbers, we know that the smallest number is in the right place. But those are details, right? For a first order approximation, it's basically n passes, each pass does n operations. So we get an order n squared. And we can improve this a little bit, right? For example, once I know that these two numbers are in the correct place, my next pass, I only have to do operations on this part of my array. I don't have to compare the numbers after that. And so as I move through further passes, the amount of work I do in this inner loop actually shrinks. And so it might be something like, you know, n minus the pass number. But this is still going to be order n squared. And if you run through the math, if I just do, you know, n passes, let's say there's 10 pieces of data, so n equals 10. Well, if I do, you know, 10 comparisons inside each pass, and I do a total of 10 passes, that's going to be 100. That's the n squared. If I embellish my algorithm so that the first time through I do 10 comparisons, the second time I do 9, the third time I do 8, and the next time I do 7, and so on, that's going to end up being 55. And it's going to be this number over 2, so it's going to be basically order n squared over 2. And that's the same thing as order n squared. Remember, these orders aren't looking at the absolute time. They're looking at, if I double n, what happens to n squared over 2? It goes up by 4. If I double n, what happens to n squared? Goes up by 4. So these are the same order of complexity. Let me write it like this, n squared over 2.
I've been struggling with this the whole semester. Could you think of it as the growth of the algorithm can potentially grow to n squared the number of things you put in as the argument for the algorithm?
Basically, so it's the time that it takes grows to n squared.
Okay, so it's time, not necessarily the growth of the algorithm.
Yeah, it's actually the growth of the time.
Okay, got it.
So if n is 10, I'm going to do 100 operations here. If n equals 20, I'm going to do 20 plus 20 times. That's going to be 400. So I double n, I quadruple the amount of work I do. Here I would end up doing 20 plus 19 plus 18 and so on. And that's going to end up being, I don't know, 210 or something like that. 220. So basically doubling.
So only the loops are adding to that. So if you had like 3 nested for loops, you'd be order n cubed.
Typically, if you had 3 nested for loops, you'd be looking at n cubed.
Okay. So PA5 would just be at order n kind of a thing then. Where n is the number of items.
PA5 has a really difficult order of complexity to figure out. I don't know what that would be. Particularly without dynamic programming, it's pretty convoluted. With dynamic programming, I think it becomes order n actually.
Yeah.
I actually put a little global inside of my style function just to see what the recursion
Cool.
is like by the time I'm done.
Nice.
And I had only put 2 items into my list, so one of them was like a weight of 5 and a value of 8, and the other was a weight of 1 and a value of 1. And without actually caching what the values were, it was 570, and when I did do the caching, it was 37.
Nice. Cool. Yeah, good illustration. All right, so bubble sort's a quick and dirty go-to. It's the only sort I've ever actually like coded when I needed to sort something. I mean, I've coded other sorts for classes, but when I've written code where I needed to sort something in like C or Java or something, I usually just code a bubble sort because it's so straightforward to code, but it's not very efficient.
You don't like the BOGO sort?
Yeah.
It seems fine for quick and dirty small data sets, right?
Mm-hmm.
You know, like if you're working with something bigger, obviously you use something better. But
Yeah, but if you're gonna sort 1,000 numbers, bubble sort's not even gonna you're not even gonna notice how long it takes. So that's usually fine. All right, so I want to talk about insertion sort and selection sort on Tuesday, and these are also going to be order n squared sorts, but they have different characteristics from a bubble sort. And then we'll start looking at sorts that do better than n squared. So this will be merge sort, quick sort, will be n log n, which will be, you know, closer to order n than n squared. So we'll start off with those on Tuesday. Keep working on PA5 if you haven't already finished it. Make sure you get that in by Tuesday morning. Come by office hours if you have questions. Finish up whatever you want to finish before presentations for SLP. And remember, SLP is Tuesday, 3 to 5. It'll be a Zoom presentation, so I'll see people there. Other than that, have a great weekend, and I'll catch everybody next time.
Thank you. Awesome lecture.
Thanks.
Have a good day.
You too.